In this lesson, we're going to investigate correlation. A correlation exists between two variables when one of them is related to the other in some way. We want to determine if there is a linear relationship between the two variables. The linear correlation coefficient is a number that describes the strength of the linear relationship between two variables. The coefficient is denoted as R when calculated for a sample. We will round R to 3 decimal places. R is always between -1 and 1. If R equals 0, that means there is no linear relationship at all. If R equals 1, then there is a perfect positive correlation, or both variables are increasing at the same rate. If R equals -1, then that means there is a perfect negative correlation, or both variables are decreasing. If we change the scale, R will not change, and the value is also not affected by the choice of X and Y. Here are some pictures of correlations. We achieve these by graphing our ordered pairs and creating a scatter plot. The first picture shows a correlation that is a perfect negative. You can see we have a -1 slope, and all of the dots line up on this line. The second picture is R equals 0, and there's no correlation. All of the points are scattered and they aren't grouped together in any direction at all. The third example shows a perfect positive correlation where R is equal to 1. All of the dots line up in a perfect line with a slope of 1. Here we see a strong positive correlation where most of the dots are clustered together where they have a trending upwards, almost like a slope of 1. The second picture down here shows a weak negative correlation, and finally another example of 0 correlation. A scatter plot is a graph that shows the paired sample points plotted on an XY coordinate grid. There are pictures of scatter plots in your textbook. Here's the scatter plot example showing daily swimming pool attendance for July. So on the x-axis we have the highest daily temperature readings, and the y-axis is the number of people in attendance at the pool that day. How many people were at the pool on the day the high temperature was 91 degrees? So between 90 and 92, I would see 91 would fall here on the x-axis, and so I'm going to find a point that falls on that line. Once I find that point, I want to go to the y-axis to estimate the number of people in attendance that day. So we can estimate about 425 people. I'm going to show how to calculate the correlation coefficient R in the TI-30X2S calculator. There are many different calculator models and brands, so if you have a different calculator, then you may need to consult your user's manual or Google the model and Google 2 variable statistics to get instructions. You can compute R by hand, but the formula to do it is quite complicated. It's much quicker to enter the data in the calculator. So on the TI-30X2S, first we need to clear data. So we're going to press second, data, and then we're going to arrow to the right to underline clear data. Then we're going to press equals. Now we're going to press second, data again, and we're going to arrow over to 2var and set the calculator to 2 variable statistics mode. Press equals to do this. Now we can enter the data in the calculator. So now just press the data button and you will enter in your numbers. Make sure that you're entering in the numbers for the x's. Press the down arrow to enter successive points. Press the stat var button to calculate, and we need to arrow to the right until we can see what R is. R is the linear coefficient. So let's calculate R for the data in this table. So our X is 3 and our Y is 5. So we are dealing with ordered pairs here. And so when I type this in my calculator, if I'm using that particular brand, I want to make sure that I type in the 3 first and then the 5, then the 1, then the 8. Other calculators are set up where you have lists, like a column, and you want to type the X's in list 1 and you want to type the Y's in list 2. This is the R that you should get when you enter the data in and you calculate your two variable statistics. Negative 0.956. Always round R to 3 decimal places. Once we know how to calculate R, we also then will need to know how to interpret our results. We will do this using Table A6. If the absolute value of R is greater than the value that we look up in Table A6, we can conclude there is sufficient evidence to support significant linear correlation. So when our R is negative, we always want to look at the positive sign of that. That's what the absolute value does. And we're going to compare it to the critical value that we get from Table A6. If R is greater than the critical value, there is linear correlation. Correlation does not imply causation. There are many other variables that could be having some contribution to the effects that we're seeing. Using averages can also inflate the correlation coefficient. R only tells us something about the strength and the direction of the linear relationships. The data may have a relationship that's not linear. And if it is not linear, R wouldn't make any sense. Using data collected from the FBI and the Bureau of Tobacco, Alcohol, and Firearms, the number of registered automatic weapons and the murder rate were obtained for each of 8 randomly selected states. The linear correlation coefficient was found to be R equals 0.885. Using a significance level of 0.05, interpret R. One thing I want to mention is if they don't tell you what significance level to use, always use 0.05. So first find the absolute value of R. So the absolute value of 0.885 is positive 0.885. Now we want to go to Table A6, and we have to remember that we have 8 randomly selected states in our data set, so N is 8. And then we want to use our appropriate significance level when we look up our critical value. So let's look at Table A6. So on this table, we want to go to our N, which was 8, and we have 2 possible critical values that we could use. Up above it tells you alpha, which is your significance level. So we're either doing a 0.05 or a 0.01. So in this test we want to do 0.05, so our critical value is going to be 0.707. So if R, absolute value of R, is greater than the critical value, then there is a significant linear correlation. So let's go back and finish and figure out what our interpretation is going to be here. So what's N? N was 8. At the 0.05 significance level, we see 0.707. We compare the absolute value of R to 0.707. So 0.885 is greater than 0.707. So we conclude that there is a significant linear correlation between the automatic weapons and the murder rate. We have to be careful about concluding anything about automatic weapons causing the increase in murder rate. Now let's use a scatter plot and a linear correlation coefficient R to determine if there is a correlation between the two variables. So I'm going to graph these ordered pairs. 0137321545. Also, I'm going to enter the data in my calculator, and I'm going to calculate the correlation coefficient so that I can interpret what I'm seeing. So first, let's find the absolute value of R. R is 0.497. Okay, so now let's go to table A6. Now if you look at this, you have 1, 2, 3, 4, 5 ordered pairs. So we want to go to n is 5, and we're going to go to the alpha equals 0.05 in table A6. So in table A6, we want to go to n is 5 and alpha is 0.05. So I'm looking at this correlation coefficient. The critical value for it is 0.878. So now we compare the absolute value of R to 0.878. And I get 0.497 is less than 0.878. This means that there is not a linear correlation. Here's the scatter plot. So you can see that the graph of these points shows that there's not a trending line going upwards or downwards. They're not really clustered together at all. So this illustrates graphically that there's no linear correlation. The table below lists the numbers of audience impressions in hundreds of millions, listening to songs, and the corresponding number of albums sold. The number of audience impressions is the count of the number of times people have heard the song. So does it appear that the album sales are affected very strongly by the number of audience impressions? When you have a table like this, always use the top row as X and the bottom row as Y. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 ordered pairs. So N is 9. So we want to enter the data in our calculator, either entering it into ToList or entering it in using the data button on your TI-30X2S, and you want to calculate your two variable statistics and find R. Here's a scatter plot. So we'll get to what R is in just a second, but this is kind of showing some type of a relationship here. They're sort of clustered together, so I'm wondering, is there some kind of a weak positive relationship? And I can't really make that determination until I compare R to the critical value in table A6. So let's find R in our calculator. When you type the data in, you should find that R is 0.796. Now let's go to table A6. At the 0.05 level, so always assume 0.05 unless you're told otherwise, the critical value is 0.666 at n equals 9. So if we compare 0.796 to 0.666, we'll see that the absolute value of R is greater than 0.666. So we can conclude that there is a significant linear correlation between the two variables. So the numbers of album sales are associated with, but not necessarily affected by, the numbers of audience impressions. Let's look at this conclusion and find the error in the conclusion. So we're given that there is a linear correlation between personal income and years of education. It's reported that more education causes a person's income to rise. The error is a significant linear correlation, indicates an association between the two factors, but there's not a cause and effect relationship necessarily. Even if there is a cause and effect relationship, correlation analysis cannot identify which factor is the cause and which factor is the effect. So just be careful about when you read reports of correlations between two variables and the reports try to say that there's a cause and effect relationship there.